Welcome. First of all, let me thank the organizers, 2 of the 3 that are here, for inviting me and giving me the opportunity to present our results here. So this talk is a kind of different topic that you have seen so far. It's on non-equilibrium transport through nanostructures, and for this talk I particularly focus on spin-dependent effects here. Most of the work has been done by Niklas Gerks, who is a PhD student in my group, and also in collaboration with another PhD student, and Martin Wegerweis from Aachen. Okay, let's start and define what I mean by a nanostructure. And the most basic setup you see here, so you have some nanostructure, and by nano I mean it has discrete quantum levels. That's the main ingredient here. And also, as a side remark, it's small, so it's spatially very restricted, so usually interactions will be important on this system. And we couple this nanostructure to at least 2 leads. Of course, one can also consider more complicated setups, but in the simplest setup we have a source lead with some chemical potential and some temperature, and we have a drain lead with some chemical potential and some temperature. And well, it's coupled, so you will have some transport through the system. And there are many experimental realizations of such setups in heterostructures, nanowires, carbon nanotubes, single molecules. So there are really many examples from the experimental point of view. As I already said, so if we have a finite bias voltage, so when μs is not equal to μd, or if we have a finite temperature bias, then usually we'll have an energy diagram like that, and we will get some transport through the system. So we will have some currents, in particular the charge current, the energy or heat current, and also the spin current. And the basic goal here is to understand the transport phenomena that will dominate here in this nanostructure. To give you a flavor of how that looks like in reality, I have here 3 different examples from experiments. So here, that's a relatively old work. You see nicely that's transport through a quantum dot in a nanotube, and you see here the differential conductance as a function of the gate voltage, which moves around these levels here, and as a function of the bias voltage that is applied. And you see here certain regions where the transport is strongly suppressed, so they are known as the Coulomb diamonds, because the suppression is actually due to the Coulomb interaction on these dots. Very recently, there has been also further work in Delft here, where you can then also look closer what is in these Coulomb diamonds, and if you really resolve things, then you can see various resonant and off-resonant processes also inside these Coulomb diamonds and outside, and you can learn a lot about the structure of your nano, about the energy levels and the relaxation processes on your nanostructure by studying all these lines here. I will come back to that. And also, what is also possible in such setups is that you can also apply a thermal bias. So for example, here you have heated up the left lead or source, and the drain is not heated up. And then you can measure, for example, the Seebeck coefficient, and therefore the thermal transport. In that case, through this molecule here. Okay, that brings me to my outline. So I will study in this talk the kind of paradigmatic model for these quantum dots or nanostructures, which is the so-called Anderson model. So I will first define it, of course. Then I will quickly go through the basic transport processes that appear in these systems, and this is all well known in the literature. Then I will really come to the new results, namely, so we studied the energy and heat transport in these systems and provided a kind of energy transport spectroscopy. I will briefly show you some results on multi-level systems to go away from this simplistic paradigmatic model. And then in the second part of the talk, I will move on to the spin-dependent transport. In particular, we will see that there can be spin current without charge currents in these systems if you choose the parameters right. Okay, but first let's go through the basic transport processes in these systems. So here is the kind of basic model we want to study. So we have a quantum dot here that has a local Hamiltonian given here. So here's the energy spectrum. So we have a single level that can be either empty, it can be occupied by an upspin or a downspin, or it can be occupied by two spins. And the energy epsilon here, the so-called gate voltage, is the energy of the singly occupied level, which may be split by a magnetic field, so you have a difference between the upspin and the downspin electrons. And furthermore, when you have two electrons on your level, then you have to pay this Coulomb repulsion U here, which is usually relatively large, on the order of milli-electron volts in the real systems. Furthermore, we have two reservoirs here that are just described by free electrons with some density of states rho naught. And we have some tunneling here with some tunneling amplitude T, which just describes electrons tunneling from one lead onto the dot and to the next lead, and vice versa. And the basic quantity to study this here is the so-called tunneling rate, gamma, which is the product of this T squared times the density of states here. And, well, h bar is equal to 1 here. We are always in the quantum limit. Good. So if we want to study this non-equilibrium transport, so we have a finite bias voltage, maybe also finite temperature bias. So we need a method that can deal with this non-equilibrium setup and also with these strong interactions on the system. The method we choose is a so-called real-time technique, which starts from the von Neumann equation for the full system. So for the full system, the dot int also the leads. And, well, this is the von Neumann equation. We have the density matrix of our system, and it's described here. And of course, since our Hamiltonian decomposes into the dot, the lead part, and the tunneling, also this Liouville operator, which acts on the density matrix, will decompose into these three parts here. And initially, or as the initial condition for our equations here, we choose a product state. So we have the dot prepared in some initial state, and we have the source and the drain leads in their equilibrium distributions. So the bias voltage and the temperatures go in here. Eventually, what we want to study is the reduced density matrix of the dot, which we get by tracing out the reservoir degrees of freedom. And this is then done in practice perturbatively in this tunneling between the dot and the leads. And we will find some rate equation for the dot occupations, or in general for the density matrix of the dot. And since it's perturbative in this tunneling, this approach here is good if we have weak coupling between the dot and the lead. So gamma, this parameter, has to be much smaller than the temperature and the Coulomb repulsion. And in general, we want to study, or in general, we can describe all time-dependent processes in this system. We can also describe the relaxation of the system. But here I will only focus on the stationary properties of our system, which are then described by this effective dot Liouvillean here, which still contains all the information about the relaxation rates of the system, which depend, of course, on the interaction strength, on the voltage, on the temperature, and so on. Yes, so, and from the stationary density matrix, we can then obtain the stationary observables, for example, the currents through the system. And as I said, one can also use that to describe the real-time dynamics and the relaxation. As a disclaimer, there are, of course, many other methods on the market to describe these type of transport setups, and they all have their advantages and disadvantages. And if you are interested, then we can discuss about that over coffee. Good, so let's go through the basic transport processes that we can see in these systems. The simplest thing is the so-called single-electron tunneling. So here we have the current as a function of the bias voltage and the gate voltage, and here's the energy scheme. And you can see that, suppose you have your system in a singly occupied state, and then you move down this reservoir here, the voltage in this, the chemical potential in this reservoir. At some point, the electron can tunnel out. The dot becomes empty. But then from the other reservoir, an electron can tunnel in, and then it becomes occupied again. And this resonance here is just single electron processes. An electron goes out, another one goes in, and you get a strong peak in the differential conductance here. So that's kind of the basic setup here. And here you see this Coulomb blockade regime, namely when you don't have enough voltage provided by your leads, then you just have no transport in this order gamma, so which is the leading order. And the broadening of the single electron processes here is essentially just the temperature in your system. If we now apply a magnetic field to get something more interesting, then, well, we see obviously that these processes here will split because the energy of the upspin and the downspin electron is no longer the same. So you get some splitting of these single electron tunneling lines. And if you consider here a cut through, for example, and calculate the spin current, then you see while here the red charge current, then when you move up here, increases, then at that point here, only the upspin electrons start to contribute to the transport, and then when you cross that line, then also the downspin electrons start to contribute, and then in total you don't get any transport of spin. The other thing you see here in the presence of a magnetic field is that also other somehow additional features inside this Coulomb diamond appear. And so next we want to look at those in a bit more detail. So if we take a cut here inside the Coulomb diamond, then where we see various things. So first of all, there is a kind of finite value of the differential conductance, which is due to elastic cotunneling processes, where you have order gamma squared, so fourth order in the hopping processes, where you only have virtual occupation of the doubly occupied or these unoccupied states. So they give rise to conductance here, which is of course much smaller than the order gamma processes here in the single electron processes. Then when you move further up, at some point the external bias voltage will be the same as the applied magnetic field. And that means that you can also have processes where this intermediate state is, for example, an upspin electron. Because the energy you need to overcome the splitting between the up and the downspin electrons is provided by the external voltage. So this is then this inelastic cotunneling processes. And well, this corresponds to the opening of a new transport channel. So the differential conductance will increase at this step here. When you move further out, then there's the so-called cotunneling assisted single electron tunneling. So this is a more complicated process. Usually you would say, well, here it's still inside the Coulomb diamond, so I will not have single electron tunneling processes. But here now the external bias can start to populate the upspin electron, and then the energy difference between the upspin and the doubly occupied, say, is no longer it's smaller than from the ground state to the doubly occupied one. So you can already have single electron tunneling processes here to the doubly occupied state and then back to the ground state. So this is also an order gamma squared process, but it's much faster because it involves these two single electron processes. And then, of course, when you move out further here, then you have the big single electron tunneling process that dominates everything out here. But by these processes here, you can already learn a lot about the structure inside your Coulomb diamond, and you can, well, see what processes are possible between the different energy levels on your nanostructure. Now, that was charge transport. Now let's have a look at the energy transport for the same. And if you compare this result here for the charge conductance with the energy conductance, you immediately notice that you have much more contrast, which is mostly due to the fact that the energy conductance is both positive and negative. So essentially you gain a sign, and therefore you get, because you have transport via electrons or holes, and therefore you also get additional information about the type of the carrier. And in general, you see here all these different processes I just described for the charge transport. You also see in the energy transport. So you have the onset of inelastic cotunneling here, which is much weaker for the energy transport. But then here you have these coset processes, which are also visible. And then here, for example, you have a process that you can hardly see in the charge transport, but you very clearly see in the energy or heat current. Good. So that's the energy transport. As a side remark, one can also apply a thermal bias by just choosing different temperatures in the source and in the drain. Then the situation would look like that, so that the first feature you immediately see is that the different single electron tunneling lines will be broadened by these different temperatures, depending on whether they are coupled to the hot or to the cold bath. But furthermore, when we zoom in here on the energy transport, then we can also see that there is a certain offset between these coset lines here, which is proportional to, well, in that case, to the temperature in the drain of our setup. So in principle, one could use that to kind of build a thermometer to obtain the temperature in the drain lead. But, and this is all well understood, and we can calculate that also analytically, kind of how that is linear here. Admittedly, from the experimental point of view, it's of course a very hard task to really detect that. As a kind of proof of principle, so far I have only discussed this most simple model you can imagine, but one can also study multi-level dots. For example, here an Anderson dot with 2 levels, where you also have an interaction between electrons on the different levels. And what you see here from that plot is that all these basic transport processes I just described to you, you can also see here at various points in this kind of bigger stability diagram. So for example, you have these inelastic cotunneling processes here and there, or you have this cotunneling assisted sequential tunneling here, and also here you have it. So all these processes that we have understood for the single electron, for single level Anderson dot, they also appear in these multi-level dots, and you can then learn something about the structure of your nanostructure. Good. So that was the first part on the basic transport processes and the energy transport. Now let's consider a more interesting setup from the spin transport point of view. And this is the spin valve setup, where we again start with this Anderson dot. But now, in addition to just this Anderson dot coupled to these 2 leads, we assume that these leads are ferromagnets. So we have some majority spins and some minority spins with some polarization P. And here in this presentation, I assume that the polarization in the source and in the drain is the same, but of course one can also do that in a more general setting. What is important though is that the polarizations or the magnetization in the source and in the drain lead, they can point in arbitrary directions, and also the spin quantization on the quantum dot can also be in the 3rd direction. So in principle you have here 3 vectors in the game, this NS, the magnetization in the source, the magnetization in the drain, and the quantization on your quantum dot. Well, still we have the tunneling rate, Coulomb interaction, and everything is as before. Now we go through, well, different setups. So first, the simplest and most boring situation is if we just have a parallel setup. So if the magnetization in the source and in the drain are just parallel to each other. And you see here we have chosen a polarization of 99%, and therefore you hardly see any difference between the charge conductance and the spin conductance, just because all the charge conductance is driven by, say, upspins. And of course also for the energy conductance, everything looks as expected. What is interesting though is that in this system, due to the finite magnetization of the reservoirs, you will get an induced magnetic field on your dot, which well, the formula is given here, and you see essential is, first of all, the polarization of the leads, obviously. But what is also important is that we have an interaction on our dot to break particle-hole symmetry. For the parallel setup, this induced magnetic field doesn't give any interesting effects because all the vectors here are parallel to each other anyway. But as I said, generalizations to different polarizations, thermal bias, and so on are straightforward. Now let's go to a more interesting setup when we have antiparallel spins. And in that case, first of all, one sees that the spin structure becomes, well, non-trivial, but also that there is a kind of zero bias anomaly in the charge conductance here, which if you go through here and take a cut, you can see. And the reason for that is the non-equilibrium spin accumulation on the dot. So you have processes where electrons hop on the dot and they hop off, but now, of course, if an upspin hops on the dot, it cannot leave the dot quickly enough because the spin direction on the drain is the opposite of it. And so you get a certain accumulation of majority spins on your dot, which then lead to a suppression or an increase of the transport. So this is all kind of old stuff, I would say. The most interesting setup, I think, is if you have an orthogonal setup where the source and the drain vectors point in orthogonal directions. And in that case, one finds that there is non-trivial transport due to the precession of the spin on the dot in this induced magnetic field I just showed you. And, well, first of all, this is also visible in the energy current and also in the spin currents itself. And now let's have a look kind of what one can learn from that. So, for example, if we consider here the charge transport, and here it's the spin transport in the direction perpendicular to the vectors in the leads, so kind of pointing outwards here. Then, for example, we can consider here a cut along that line in our stability diagram, and this is then shown here. So the black line is just the charge current, and we see it has a non-trivial behavior here. You have here the set line, here you have the other single electron tunneling line, and in between everything is suppressed. And this is this induced magnetic field in the direction of the drain vector and in the direction of the source vector. So, for example, if we sit here directly at the middle here, then we see that this magnetic field just points in the direction of the magnetization of the drain. So it's parallel to ND here. So there is no precession of the electron spin in the ND direction. So the spin comes in from the source. It's perpendicular to this induced magnetic field. And, well, then there is precession, but there will be no component of the electron spin will be generated in the direction of ND. So in particular, the spin current in this ND direction is 0, and that's exactly what you see here. If you go a little bit away from this middle here, then you have a more interesting situation. Now, for example, the induced magnetic field will point in that direction here, and that means that you get some non-trivial precession of your electron spin on the dot, and that then also means that you get a non-zero spin current in the direction of the drain lead and also in this perpendicular direction, as you can see, for example, here. And so you can move through here and see all the different angles and how everything works together with these precessions. Let's take another cut. If we take a cut through here, so then we have here this Coulomb blockade region. And the important thing to notice here is that while the charge transport in the Coulomb blockade region here is 0, or essentially 0, we get a very strong spin transport in the direction perpendicular to the magnetizations of the reservoirs here. So we really get spin current without charge current inside that region here. Good. So that was what I wanted to say about this spin valve setup. And in the last 3 slides, let me present something rather new. And if you want to know more details, then I would like to refer to the poster by Niklas, namely a controllable spin valve. So how can we achieve control of this spin current without having to rotate this, the magnetizations or things like that? Well, we can add a kind of third electrode, a base electrode, with some hopping TB here, and the tunneling rate gamma B is assumed to be much larger than gamma. And of course, we have a chemical potential mu B here. And in this setup, we can then also study the transport, and that's what we find. So first what we see is that there are of course new resonances because we have a new energy in our system given by this chemical potential of the base voltage. But we also see, if we compare this case here with this case, that obviously somehow things get controllable by changing this chemical potential on this base gate. And if we, for example, consider this point here in the stability diagram and then vary this chemical potential in this third lead, then we see here in the Coulomb diamond regime that we have hardly any charge transport, and indeed again we have spin transport, and we also see that we can control it to some extent, let's say. So again we see large spin currents without charge currents, and everything in a controllable setup by changing this chemical potential. Good, that brings me to my conclusion. I showed you a lot of stability diagrams and plots. I used them to discuss the basic transport processes in these quantum dots, namely single-electron tunneling, elastic and inelastic cotunneling, and cotunneling-assisted single-electron tunneling. There are even more that I didn't discuss of higher order. If you want, you can ask me in private. What I also showed you is that all these processes here are also well visible in energy or heat transport. And then I showed you that the spin precession in the induced magnetic field due to magnetic leads gives rise to non-trivial spin currents. In particular, there are regions where you have strong spin currents without charge currents. And well, in the end, I showed you how to control that in a kind of three-terminal setup. Okay, thank you very much for your attention.